Okay, so last lesson, we had a little tour through the universe, just to make sure we're okay with some of the words. The word universe refers to everything that exists. By definition, then, everything is inside the universe, and the question of what is outside the universe is a meaningless question, because by definition, if it's outside the universe, it's inside the universe, because the universe is everything that exists. Okay, so the universe is everything, and then it's largely comprised of a very large amount of empty space, but even empty space has got the odd proton whizzing around through it, so there's no real such thing as true emptiness. There's even something in the depths of space, but then obvious things out in space are huge islands of billions of stars called the galaxies. And these galaxies float around in space all together, all these billions of stars, and these collections of stars form galaxies. Some of the galaxies hang around in clusters of galaxies. Some of the clusters of galaxies hang around in superclusters of galaxies. So there is some large-scale structure to the universe. Much more mundane scales around each star, there appears to be leftover material that never made it into the star itself. And over time, that leftover material became planets around many of the stars we already know. And then some of the planets have moons, and some of the planets have life. Well, at least one of them anyway. So that's what's out there. What we need to move on to as GCSE students is a little bit more than that, though, because that's kind of what you did in year 7, what's out there, and putting names to things. As GCSE students, we want to start learning some of the science. So how does science get involved? So there are 2 types of scientists that are interested in what's up there. So the first are astronomers, and astronomers are observationalists. They look and they catalog and they look for patterns and they look for processes and changes, and they write it all down and record it. And that is the job of the astronomer, to develop better and better viewing opportunities. So we started with visible light, we moved on to radio waves. Now we observe in all areas of the electromagnetic spectrum. We began with ground-based astronomy, but we've moved into not only telescopes in space, but actual probes and landers and rovers that go to other planets and have a little look around. This is all the job of the astronomer, to look and to catalog and to try to make sense of it. Then there are the cosmologists, and the cosmologists take the universe as a big process with lots of complicated things going on inside it, and they try to figure out the rules. They try to figure out the physical laws that underpin everything that is happening. When the astronomers say, hey, did you know what? Stars come in all different shapes and sizes. Well, sizes, different colors and sizes. It's the cosmologist's job to go, hey, that's an interesting observation. Let's try and figure out why. When the astronomers say, the stars seem to hang around in hundreds of billions in these groups, which we're going to call galaxies, the cosmologist's answer is, well, that's really interesting. Let's figure out why. Even the biggest questions, like, has it always been like this? Humans are looking up now, maybe for the last few tens of thousands of years we've been looking up, but we've actually only got data for the last couple of hundred years since we started writing it down and looking properly. So we've just got a couple of hundred years worth of data. Well, is the universe only a couple of hundred years old, or has it been here a lot longer than that? In which case, has it always been like this? Or is it changing as time goes on? And on the subject of always, is it always? Has the universe always been here? Or did it have a beginning? Will it have an end? These are all questions that cosmologists try to answer. And it's these questions that we're going to have a little look at over the next week and a half or so. We're going to start today with one of the fundamental observations, which is that we are stuck to the Earth. The moon is stuck to the Earth in orbit around it. The Earth seems to be stuck to the sun or in orbit around the sun. The sun seems to be in orbit around the center of the galaxy. The Milky Way galaxy seems to be attracted to another galaxy that's really near to us. Well, I say really near to us. It's about 50 times further away than the diameter of the galaxy. And I did tell you it would take 50,000 years for light to cross the galaxy. So Andromeda is kind of 250,000 light years away, so it's not that close. But even at 250,000 light years, we seem to be hanging around a whole other galaxy. So why is this? Why does matter seem to hang around with other pieces of matter? This was the starting point for cosmology, and it began with our friend Isaac Newton. So you've been reading that and writing it down. Newton's big idea, and it's a massive idea. Massive, no pun intended. The idea cannot be, bigged up enough. He had this vision that the reason that you and I are stuck to the Earth is exactly the same reason why the Milky Way galaxy seems to be hanging around with the Andromeda galaxy. I mean, how big is that vision to connect what's happening down here at a human scale with something up there 250,000 light years away? I mean, 250,000 light years. Humans weren't even in their current form when the light that we're seeing now set off from Andromeda. It's just ridiculous how far away it is, and yet Newton is drawing parallels. And what he is saying is that every piece of matter in the entire universe, no matter how far away it is attracted to every other piece of matter in the entire universe. That is just a crazy idea. And yet, 300, 400 years since he proposed it, we still believe it to be true. It's a crazy idea. So just think about, I don't know, you're probably sitting at a table right now. There's probably a chair under you. So the chair and the table, they are aware of each other, even though they're not touching. The atoms in the table know that the atoms in the chair are there. And they're desperately trying to pull towards each other. The chair is attracted towards the table. The table is attracted towards the chair. Neither of them move because each of them is way more attracted to the Earth, however, which brings us on to some rules about the attraction. So the force of attraction, says Newton, goes down when objects get further apart. So the chair is way more attracted to the table than it is to the Andromeda galaxy. The force of attraction is bigger the more gravitational mass the matter has. Now that's called kind of just a placeholder for no idea what this is, but it's obviously got some of it. So like electric charge, it's a fundamental property of matter. Protons, neutrons, electrons, atoms, molecules, people, chairs, table, they collectively have some gravitational mass. We don't know what it is or where it comes from, although the great people at CERN, the particle physicists, are making great headway, so I'm told. But whatever this property is, it's the ability to attract and be attracted by other pieces of matter. The chair has got a certain amount of mass, the table has got a certain amount of mass, and they're doing their best to attract each other across the relatively small separation between them. Unfortunately for each of them, or fortunately, depending on how you look at it, the Earth beneath our feet has got way more mass than either the chair or the table. So if anyone's going to win the attracting contest, it's going to be the Earth. And that is why the objects in our lives are stuck to the ground and not stuck to us. So it's nice to think that everyone you've ever met is very attracted to you. but it takes the shine off it a little bit when you realize that they're more attracted to the big lump of rock that they live on. So gravity, for short, Newton's universal theory of gravitation, to give it its grand name, is the idea that all matter is attracted to all other matter. It weakens with separation, but it's true no matter what the separation. And that's why the moon orbits the Earth, because the mass in the moon is attracted to the mass in the Earth. And the Earth, similarly, is attracted to the sun. And the sun, similarly, is attracted to all the other stars and collectively to their center of mass in the middle of the galaxy. We actually wonder even if there's something very, very massive indeed at the center of the galaxy. We'll come on to that next lesson. Then we've got the idea of the galaxies attracting each other. The separation is truly vast, but the masses of the galaxies are vast as well, and it makes up for it. Gravity is this unifying idea in physics. And from a cosmologist's point of view, gravity is the fundamental force governing the entire large-scale operation of the universe. We are not interested in electricity or magnetism or friction or any of the other forces that you would like to name. If you're a cosmologist, the only force that's important to you is gravity. And so understanding everything comes from an understanding of gravity. So let's have a little think about why stuff orbits the Earth. So here's an Earth, well, kind of a globe. I made you a satellite model. Do you like it? I Blue Petered it right up. Okay, so let's think about a satellite on the ground in Russia before it launches. So there's the satellite on the ground, and the reason that it is on the ground is because the Earth has a lot of mass, and the satellite has some mass, and the huge mass of the Earth and the little mass of the satellite are attracting each other. They're quite close together, so it's quite a lot of gravity, quite a lot of force. To get the satellite off the ground, we need to apply an opposite force. We've studied forces. You know that we need a non-zero resultant force. At the moment, the force of gravity is pulling the satellite down, and the normal contact force on the ground is pushing it back up again, and it's completely balanced. If we want the satellite to go up, we need to give it more upwards push. So we strap rockets to it, and we make the rockets push it up with more force than the gravity is pulling it down. And up the satellite goes. But as soon as we turn the rockets off, it's gonna come back down again. So what we need to make sure we do is when we launch it, up, up, up it goes, we also launch it sideways at the same time. So why does that work? Well, think about throwing a stone. This is a really big stone compared to the Earth, but nevertheless, say you pick up the satellite and you just lob it and it goes whee, and it comes back down over there. Well, if you throw it a bit harder, you might be able to throw it so it goes whee and lands all the way over there. Because ultimately, you got to remember, the Earth is a sphere. Throw it really hard, and you might be able to get it all the way around to what, there? That would be a good throw, right? Get halfway around the Earth. Give it a seriously large throw, and you are going to throw it so hard that round and round and round and round and round it goes, and it comes back and hits you in the back of the head. That's kind of what an orbit is. An orbiting object is falling all the time. It's just moving sideways at the same time. And because it's traveling in a circle, the ground is never quite there when it tries to fall down. So it does fall down, but there's no ground to hit. Now it realizes the ground's over there, so it tries to fall down again, but while it's falling down, it moves again, and it does fall down, but there's no ground there anymore, because it has to remember, oh, look, the ground's up there now. Orbiting is controlled falling. You fall in such a way that the ground is never there when you get there. It's a bit weird, but it is the way that we put satellites into orbit. It's the way that the moon orbits around the Earth, constantly falling down, but traveling sideways at the same time. The Earth going around the sun, trying to plummet into the sun, but too busy going sideways at the same time. I'm going to rub that off and draw you a picture of this. But the basic idea is that gravity really does hold things in their orbits. It doesn't have to succeed in pulling things together if one of the objects is moving at the same time. And I'm going to move out of the way in case you're still copying that down, and I'm stopping you from doing so. Another way to think of it is kind of some artificial gravity, not real gravity. So imagine that you have a piece of string. You might even have a piece of string. You could do this when I finish yabbering, and tie something to it. I suggest something kind of soft. And if you whirl it round your head, in a sense, whatever it is you tied to the end of the string is orbiting your head. And why is it orbiting your head? Well, not due to the gravity, because you don't own enough mass, and neither does whatever you tied to the end of the string. So it's not a gravitational force. It's the tension in the string that's holding it. And you are pulling on that string. If you let it go, off it would go. So you are pulling on that string, but you never manage to pull the object into you because it's too busy traveling sideways at the same time. In fact, if you want a really cool demonstration of this, if you own a bucket with a reasonably good handle, half fill it with water and go outside in your garden, the garden's important, after this lesson, and just take the bucket and just do that with it. And if you whirl it round fast enough, two things will happen. One, you will feel in your arm the force that you are having to hold the bucket with. But two, the water will orbit your head instead of, or orbit your shoulder instead of landing on you, as long as you keep it moving fast enough. Have a go after the lesson. Okay, I'm assuming you've done that now, so I'm going to rub it off. The lesson's being recorded, so if you didn't quite get it, you can play back later. So orbits. So we can use real objects if you'd like. So this might be the sun, and this might be the Earth. Or it could be the moon and the Earth. Could be the sun and the center of the galaxy. Could be a bucket of water in your head. When one object orbits another, you need a force to make it happen. And we can appeal to physics we already know as well. Back in year 10, we said that an acceleration is when the velocity changes. Well, here's the velocity. But a little bit later, that'll be the velocity. And then a little bit later, that'll be the velocity. And you can see that the direction is changing. Even if the speed stays the same, it's still accelerating. because velocity is a vector that has magnitude and direction. And even if the size, the magnitude of it stays the same, the direction doesn't while it's in orbit. So because the velocity is changing, there has to be an acceleration. And then we also learned that accelerations are provided by unbalanced forces. And here is the unbalanced force. Now, if you opt to do an A-level in physics, we spend a very, very long time on this. 4 weeks on gravity in orbits. And we will talk about why it has to be the case that that's actually a right angle. The force always points towards the center of the orbit, but the object is always moving around the orbit. And in actual fact, most orbits are practically circular. I say practically circular. You're GCSE students rather than A-level students. And so it's an okay approximation. Certainly if you tie something to a piece of string and whirl it around your head, you're not letting the string get any shorter or longer. So that really is a circular orbit. The Earth traveling around the sun, it's around about 0.1% of truly circular. The name of the slightly not circular shape is an ellipse. So you might have heard of an ellipse. You might have known that the planets travel in elliptical orbits. But honestly, it's less than 1% away from a circle. So, you know, there's the circular orbit. There's a really extreme ellipse, a squashed circle. But you wouldn't be able to tell that the planet's orbit wasn't circular unless you looked really very carefully indeed. So at GCSE, we're going to assume that the orbits really are circular, even though it's like less than 1% not. We're going to just let that go by. If you want to learn about elliptical orbits, come join us for A-level physics and we'll talk about it then. But circular orbits, and so you can kind of think of this as in the direction of a radius, and this is more of a tangent. And you know from maths that a radius and a tangent are at right angles to each other. If this V was pointing in a little bit, that means that the orbiting object would be getting closer and closer to the middle, which would be crash and burn time. If it was pointed out a little bit, it would be spiraling off into space. So for a confined orbit, it needs to travel at a constant distance. And that means that this is tangential. And the force is always towards the other piece of matter. So it's a weird idea to think that this is a force and it is providing an acceleration. But unlike the one-dimensional examples that we studied in year 10, you know, Granny pushes a car and the car accelerates in the direction of the push. That was a one-dimensional situation. We never got Granny to push a car in a circle around a traffic island. She'd have had a whole different experience. And so this is a two-dimensional example of F equals ma. It's still an acceleration, even though it's the velocity's over in this direction. So in terms of making notes from this board, what do I want you to take from this? I want you to know that the force due to gravity is at right angles to the velocity. And that the force is necessary because the direction is changing and therefore it is accelerating. And therefore we do need an F for F equals ma. And I also want you to note that certainly at GCSE, we are going to assume that orbits are circular, even though it's a tiny little lie. It's only a little tiny one and it doesn't make any fundamental difference to the analysis. I'm just going to give you a minute to finish writing that down. Okay. Now, if you have whirled anything around your head recently, if you were in school, I would be giving you bits of string with little bits of rubber on the end, and you'd be outside whirling things around your head. So by all means, have a go if you want to. You'd have been doing it in school. Just like I say, make sure you hold on to the string and tie it on really tight onto the object. If you do whirl something around your head, if you've ever done that, you might know that you have to hold on more when the object is on a really tight circle or when it's traveling really fast. And why is that? Well, imagine a tiny little circle. Then say the object moves from there to there in 1 second. Then that's a huge change in velocity. It's completely reversed its direction by an entire 180 degrees. But if you think of a bigger circle, an object traveling at exactly the same speed might only get to there in, can't really see those arrows, can you? Let me draw it bigger. Might only get to there in the same 1 second. It's traveled the same distance, but because this circle's bigger, the velocity hasn't changed direction by as much. This one changed a whole 180 degrees, but this one has just changed about 30 degrees. So when you're traveling around a big circle, your change in velocity per second, your acceleration, isn't as big. Or what if you're traveling really fast? Well, if you're traveling super, super fast, well, actually, we don't need both pictures. That's how far you might go if you're traveling slowly. But what if you're traveling really fast? Well, if you traveled that far when you were going slow, you probably travel a lot further if you're traveling fast. And again, now the angle is a lot bigger. The velocity change has been a lot more. So if you travel fast, or if you travel close, if you orbit close, you need a way bigger force to hold you in place. Well, I just told you that gravity is a force that depends on distance. And so at this point in space, there is a certain force. It depends not on the object that's moving or how it's moving. It's at that point in space. If you place a mass there and a mass there, and there's the difference between them, gravity is a force that depends upon separation and the two masses, nothing to do with the speed. So at this point in space here, there is a certain force. If this object is traveling too slow, it won't need that much force to hold it in orbit. And there'll be a whole load of leftover force that's not just going to hold it in orbit, but going to drag it into the ground. So if this thing travels too slow for that size force, going to crash and burn and spiral into the sun or the earth, and it's game over time. Or if this object travels too fast, well, it needs a way bigger force to hold onto it. But there's only that much force because it's that separation from the orbited object. So if there isn't enough force to hang on to it, the opposite will happen. Off it'll fly into space, disappear, never to be seen again. So the next thing that I need you to note is that at any particular place, there is a perfect speed at any distance. Let's write distance instead. There is a perfect speed to stay in orbit. If you're close to the ground, you've got to be traveling fast, because you need a big force, and there is a big force. If you want to be orbiting a long way away, you better be orbiting slow, because there's only a little force out there, far, far away. And it's only if you travel slowly that that little force will be able to hang on to you. So Mercury is zipping along. Nearest planet to the sun, there is huge amounts of gravity that close to the sun. Mercury is hurtling along at a blistering speed. And it's really close to the sun, so it doesn't have very far to go anyway, which means Mercury whips around the sun. A year, I can't remember how long a year on Mercury is, but I do remember that a year on Mercury is shorter than a day on Mercury. Meanwhile, go out to poor little disowned dwarf planet Pluto. There is so little gravity out there, so little force, that Pluto has to trundle along really slowly, because if Pluto was going at any other speed, it would either escape or it would crash and burn. So the inner planets travel very fast, and they don't have very far to go anyway. So a year for an inner planet is quite short. The outer planets, they have to go really slowly, and they've got a long way to go because it's a big circle. So a year for the outer planets is very long indeed. When we launch satellites into space, we have to pick the speed that they travel at to match the height we want them to be at. So if we want a satellite that's really close to the Earth, we need to launch it traveling really fast, because otherwise it will crash and burn. Gravity will win and drag it back to the ground. If we want a satellite to be very, very high in the sky, we need to launch it traveling really slowly, because if we make it go too fast, it'll fly away because there's not enough gravity there to hold on to it. So this is the other thing about orbits. There is a perfect speed. Gravity is a great force, it really is, but it's a fixed force at any distance from the sun or from the Earth or from the galactic center. You've got to be traveling at the right speed. If you travel any slower, you're going to get sucked in and you're going to crash and burn. If you travel any faster, you're going to not be able to be held in orbit, and you're going to zoom off and leave orbit altogether. So all the satellites that we've launched into space, we've had to pick the speed that we launch them with. I don't mean upwards, I mean sideways, so that they stay where we put them. And any moons that Earth might have had, maybe once upon a time we had 10 moons, but some of them traveled slow and crashed and burned, and some of them traveled fast and left. Only our moon remained, the one that happens to be traveling at just the right speed to stay with us. Maybe the solar system once had 20 planets, but some of them plummeted into the sun and some of them escaped out into the outer solar system because they were traveling too fast. You've got to be traveling at the right speed. Okay, just a little note about artificial satellites. We do like some satellites to travel really fast. These are the satellites that travel around the Earth in just a couple of hours, which means in a day they might orbit the Earth 8 times. Because they're traveling so fast, they zip across the sky. If you've ever looked up at nighttime and you've seen a little sparkle of light zip across the sky, it's the sunlight bouncing off the solar panels. Satellites tumble a little bit sometimes, and so it twinkles as it goes. These are the satellites that we've launched fast because they are low orbit satellites. They zip across the sky. They don't hang around. We use these satellites for things like spying on other countries, because if the satellite whizzes over the country and doesn't really hang around, it's not like the government of the country can say, hey, you've parked a satellite above our country, you're spying on us. You just say, no, I didn't. I just put a satellite up in space and it happened to travel over the top of your country for a couple of hours. It's not like we were taking pictures while it went past or anything. Other kinds of satellites, though, we do want to hang around. Our satellites. So here's the UK. You in your house watching your Sky TV or whatever you're doing. Well, you'd be really irritated if the satellite beaming down your Sky TV was just sending you a really crucial part in whatever you're watching and then decided to zip on past. Well, we can't broadcast to you from the other side of the world. So we need some satellites to travel at the same speed as the ground, so that the satellite takes 24 hours to go around the Earth, while the Earth takes 24 hours to go around the Earth. That means that they'll be traveling together. You should be aware of these things. You should be aware of the fact that gravity dominates the universe. It's the most important force for the out there stuff. You should know that it's a distance-dependent force, and that has an effect on what can orbit what. Need to be traveling at the right speed. Sometimes we put that to our advantage for satellites at different heights because we want them to do different things. Other times it just allows us to explain the way things are, the reason that the planets are in the orbit that they're in, the reason that the sun is in orbit around the galaxy, the reason that our galaxy is orbiting around Andromeda, or Andromeda's orbiting around us, whichever way you want to look at it. Today's lesson has been about this idea that gravity dominates. And I've given you a couple of little details, but it's that take home that I want you to have for next lesson. Gravity dominates. It's the most important force.